Hey everyone, welcome back to the placement series. Today we'll be looking at the third question of Rocketlane, which is based on sorting a binary set of binary strings. So let's read the question first. Given a set of binary strings denoted by positions of the set bits, sort them in descending order and return the indices as they appeared in the original array. So first of all, let's see what does it mean by binary string. Binary string basically means a number denoted in base 2. For example, 10 can be denoted by something like 2 plus 8, right? 2 plus 8, which is 1 0 1 0. So this is the binary representation of string 10, and we'll call this as the binary string 1 0 1 0. So this is what a binary string means. Okay, that's done. And then denoted by positions of the set bits. So what is a set bit? Whenever there is a 1 at a position x, we call the x position as set. For instance, in the given example 10, we have the bit 3 and 1 as set, while 0 and 2 is not set. So the corresponding positions of the set bits would be 3, 1 or 1, 3 in any of the order if you might want it. So that's what set bit means. And the rest of the bits are not set. Sort them in descending order. So descending order of the value basically. And then return the indices as they appear in the original array. So what do you mean by that? So let's take one example and see. We have the original array 1, 2, 2, 0 and 1, 3, which denotes the positions of the set bits. For example, the set bit 1 and 2 are set, which means 0th bit is not set, first bit is set, and second bit is set. And for the next one, we have 0th bit and second bit are set. 0th bit is set, first bit is not set, and the second bit is set. And for the third one, we have the third bit and the first bit are set, and the rest of the bits are not set. So first bit is set, second bit is not set, and the third bit is set. And these are the three binary strings we have, and the value of this would be 2 power 0, 2 power 0 times 0, which is 0, 2 power 1 times 1, which is 2, and 2 power 2 times 1, which is 4. So 2 plus 4, we have a value of 6, occurring at the index 0. So this is the final array we have. And basically we can sort them based on their values, and we then return the indexes. So sorting them based on their values will give us 10, 2, 6, 0 on reverse order absolutely, and 5, 1. 5, 5, 1. And we'll return the indices around, which is 2, 0, 1. And this should give us the answer, which is 201, as we saw here. So the question seems pretty simple, right? So let's see where the actual problem arises. Say instead of having 1, 2, something you will have something like say have something like 101, 102. What will happen in the case? Let's see. What will happen in the case? Let's see. Well, the value of this would be 2 power 101 plus 2 power 102. And the problem we have is, in C++, the largest integer container called the unsigned long int, which means goes from plus 0 to plus 2 power 63. The maximum value possible for the unsigned long int is 2 power 63. And we have something like 2 power 101 inches. And basically for Python, the value would be somewhere around higher, but it would still be less than 1000. So on this case, what can we do? We basically can compute this, because we cannot even store 2 power 101. If we can store 2 power 101, how can we even compute it? That's the question, right? So what actually happens is that when you go beyond 2 power 63, so assume the size is somewhat this is the size, and everything will be set to 1 at 2 power 63, right? Everything will be set to 1, and when you add plus 1 to it, everything will become 0. This is a case where we call as integer overflow. Where if we add something about the maximum value possible, it will revert back once from the maximum to the minimum value possible. It will go to the minimum value possible from the maximum value. This is called integer overflow. Max plus 1 will give you minimum values possible. This is called the integer overflow. Because we cannot store 2 power 1 and we cannot directly compute it. So what solution do we have? What should we do to solve this question? We basically should make sure that we do not compute anything. Yeah, basically that's it. So we should not compute the value but sort them. So, well, how is that even possible? Alright, assume we have two binary numbers A and B, and the xth bit of A is set, or the nth bit of A is set, and the nth bit of B is not set, and the rest of the bit for A is 0, while the rest of the bits for B is 1. So, what does it actually say to us? So, let's compare. The value of this would be, value of A would be 2 power n, and the value of, okay, and it extends, goes on, and the value of B would be 2 power n minus 1. So, what can we actually infer from this? No matter, no matter, no matter what comes after the most significant bit, no matter what comes after the most significant bit, if the most significant bit, most significant bit is 1 for one number and 0 for another number, the number having 1 at the most significant bit would be always greater. So A would be always greater than B, regardless of whatever comes after the most significant bit. So suppose A and B. Suppose you have two binary numbers, once again A and B, and till, let's say, till some index x, till some index x, and yeah, till some index x, both of these are same. Both of these are same till the index x, and A has a value 1 and B has a value 0. And what should be greater in this occasion? Think for a moment. So A can be set as s plus 2 power x, and B can be set as x plus 0 plus whatever that comes after. So the value of A would be s plus 2 power x plus s1, and the value of B would be s plus 0 plus s2. So A would still be greater than B. So how do I say that? Let's see. The least value possible for, let's assume the least value possible for S1, which is 0. And the largest value possible for S2, which is 2 power x minus 1, as we talked earlier. Because 0 to x, the summation of one every bit 1 would be 2 power x minus 1. So the value of A would be, on the occasion, s plus 2 power x. And the value of B on the occasion would be s plus 2 power x minus 1. So what can we say from this? What can we say from this? So when two binary numbers A and B, have, when two or more, let's assume more also, when two or more binary numbers A, B, C, D, E, F, G, H, etc. have the same number of set bits from most significant bit up until x, and at the position of x, some has 0 and some has 1s. The ones which have 1s will always be greater than the ones which have 0. For example, at the xth bit, A and C have 1 and B has 0. On that occasion, A comma C would be greater than B. What about A and C, Jagan? So we cannot say anything particularly about A and C, but we can say that A comma C would be greater than B. Both A and both C would be greater than B. So that's what I can say here. Okay, so let's put the skills we have learned into place, or the concept we have learned. Let's see where we can actually use them. So we do know that the numbers which have 1 at the set bit as the most significant bit would always be greater than others which do not have 1. So on this occasion, we do know that these four numbers would always be less than the other three numbers, because they have a set bit 1 and the others do not have. So what we can basically do is we can then separate them into two separate groups. The ones which have 1 at the MSP and the ones which do not have 1 at the MSP. So the two groups there would then be 0, 0, 0, 0, 0, 1, 0, 1, 1, and 0, 1, 0. And the other group would be 1, 0, 0, 1, 0, 1, and 1, 1, 0. So now that we have compared the most significant bit, let's go to the next bit. Let's go to the next bit now. And we can say that the right hand side one should always be greater than the left hand side ones. So let's go to the next bit now. And for the next bit, we do know that these two have a set bit at 1 at the first position, and the other two do not have. So let's separate these into two separate groups once again. The ones which are 1 at the MSB and the ones who do not have 1 at the MSB. Where MSB is the first place right now because we had already computed the second place, and all of them have the same number till at the second place. So the ones which are less will be 0, 0, 0 and 0, 0, 1. We have compared these two places now. We have compared these. Sorry, my bad. But here we compared this place. At here we compared these two places. And the right hand side one should be 1, 1, 1, 0. So now we have computed the first and second place. Let's compute the last place now. And the ones which have 1 would be greater than the ones which don't have 1. So obviously this would be less than this. So at left place we have 0, 0, 0. At right we have 0, 0, 1. And for here at and here and for here we have 0, 1, 1, 0, 1, 0. And to the right we have 0, 1, 1. So now we have drawn the structure for these many ones, and we cannot split them further because they are all of groups of size 1. So let's now split these once again, and we do know that these are greater than this. This is greater than this. This is greater than this, and this is greater than this. And we have finally computed all the values. And for now, we can say for certain that everything that is on the right would be greater than the left. So obviously, this is greater than this one. And obviously, this is once again greater than this one. And obviously, due to the initial split, we have this is greater than this one. So what do we have here? What do we basically have here? As you can see, we basically have a descending order sort with this guide here. So descending order sort with this guide here, which means 110 greater than 101 greater than 100 greater than 011 greater than 010 greater than 001, which is once again greater than 000. So value of this would be 0, 1, 2, 3, 4, 5 and 6. So basically we now have a sorted list with us. So how do we actually perform the sorting without even computing the values, as you can see here. So how did we actually do it? We use the concept of most significant bit having 1, and the ones which have 1 at the most significant bit and ones that do not have 1 at the most significant bit, and then we split them into two groups, the ones which have 1 and the ones which do not have 1. And we said that the ones which have 1 will always be greater than the ones which do not have 1. And among the ones which had 1, we once again said that to compare the next bit, to compare the next most significant bit, and we then once again split into two groups and two groups and two groups and so on and so forth until we have only one node at each of the leaf levels. On which case, the ones which are on the rightmost part will be greater than the ones which on the so the ones which are at the left. So basically, we did that. Hey guys, so welcome back once again. And today I'll be coding the solution for it in Python. And you can the logic will be basically same area, so it does not matter whether you're coding it in Python or C++. So let's start without wasting any time. And so basically I have the input of binary strings with us here, and the corresponding the binary representation and the corresponding given representation actually. And yeah, so that's for starters. And so what do we need to know beforehand? We need to know the level possible of we need to know the number of levels the binary tree has at the starting itself. So why do we need to have that? Because we start at the most significant bit, right? If we start here, we can just keep on inserting. But if we are starting here, so we need to know the maximum possible level of MSB. For instance, if we didn't have this line and this line, the maximum possible value of MSB would be 3, right? Because everything will have only 4 bits totally. So yeah, so we need to know the maximum possible value of MSB before we start inserting. which will be the level basically of the tree. So for now, the level of the tree will be 5. At for fifth level, starting from the fourth index is set or not. So I'm starting with the root here, and then the fourth bit is set, and then the third bit is also set, and then the second bit is not set, and then the first bit is not set once again, and then the zeroth bit is also not set because 3 comma 4 is 0 0 0. So at last we have the index. The index of this will be 0. So this is the fourth bit, and this is the checking whether the third bit is set or not, and this checks whether the second bit is set or not, and this checks whether the first bit is set or not, and this checks whether the zeroth bit is set or not, and finally we have the index that's here. So let's insert 1 comma 2 now. Is the fourth bit set? No, fourth bit is not set, so we'll go left. Is the third bit set? No, the third bit is also not set, so we'll go left once again. Is the second bit set? Yes, the second bit is set, so we'll go right. Is the first bit set? Yes, the first bit is also set, so we'll go right once again. Is the zeroth bit set? No, the zeroth bit is not set, so we'll go left. And this will have an index of 1, right? This will have an index of 1. So let's insert 3 comma 1 now. Is the fourth bit set? No. Is the third bit set for 3 comma 1? Yes, the third bit is set for 3 comma 1, so I'll go left. So I'll go right, sorry. Is the second bit set? No, the second bit is not set, so I'll go left. Is the first bit set? Yes, the first bit is set, so I'll go left. Right. Is the zeroth bit set? No, the zeroth bit is not set, so I'll go left. And now I have the index of this, which is 2. And let's insert 3 comma 2 now. The third bit is the fourth bit set? No. Is the third bit set? Yes. Is the second bit set? Yeah, the second bit is set, right? So I'll go left. I mean go right. Is the first bit set? No, the first bit is not set, so I'll go left. Is the zeroth bit set? No, the zeroth bit is not set, so I'll go left once again. And finally I have the index 3. And then let's insert 4 comma 0 now. Is the fourth bit set? No. So I'll go, the fourth bit is set, so I'll go right. Is the third bit set? No. Is the second bit set? No. Is the first bit set? No. Is the zeroth bit set? Yes, the zeroth bit is set, so I'll go right. And I'll go right, and I have finally last index is 4. The tree looks a little bit messy, but yeah. So this will be a required tree structure. So first we'll just check whether the fourth bit is set or the third bit is set, and so on and so forth up until the last bit, which is 0. So that's what we'll be doing. For this, we need to know the maximum possible level of the maximum level possible. So let's go into the tree node. The tree node will basically have a right child and the left child and an index. For the others, the index will be represented as -1, and for the leaf node, the index will have the specific values. And for the class and for the tree, the root will be a tree node, and the level, and it will also have the maximum levels possible, so we can insert it easily. So let's start insert now. So to insert what and all we need to know. To insert, we need to know the number of set bits, whether or not it's set. So let's call it set. And we also have to pass the self as the argument. It's just a syntax. So in order to insert, we have to pass the wherever there is a set bit. So let's call it ACDD. And so yeah, if I say, I suppose you have a string called 3 comma 4, and you have every time you have to check whether 3 is present, 4 is present, 2 is present, and at worst case it will take n of time, right? So I don't want that. So what instead I will do, I'll instead convert it into a set where if I want to check if 4 is present or not, it will be just done in a n of time. It will be done in n of time. So I converted it into a set basically, and then what I'll do, I'll start from the max level. Oh, okay, let's start with the what is equal to self dot. For I range, I will go from the maximum possible bit up until the minimum possible value, where it is -1, and then I'll decrease the step by each time. Self dot level, sorry, it should be level. Let's call it so that just we know what variables are present. Level is in set, If the current level is present in the set bit, I'll go to the node of write. And to go to the node of write, I first need to check the write node exists, right? So I'll check that if the write node exists, I'll go to the write node. Go to else I'll create the write node. Dot write, go to tree node, and then I'll go to the node. If it is not in the if it is not set, then I'll go to the node of it. So just you have to copy this and then convert it to node of it. So now I have traversed up until the last level, and what I'll do now is basically simple. I'll just say the index of this would be index. So I have to pass the index also. I forgot. Let's pass the index also, and the index of the and as I have finally passed through and come to the last level, I'll just have the and the index set to be what the index value is basically. So yeah, just the index. So that's for the insert function. Let's go for the sorting function. And what I'll take this as an argument because the tree is already where I have this. So what do we have to do in sort basically? So in sort basically what we are doing is what we are doing is we start from the most significant bit and go until 0. And we do know that the right for each node the right child is always greater than the left child. We know that, right? So we have to traverse the right child first and then insert the rightmost child and then go like that. So we saw that earlier. So at each level we need to traverse the rightmost level first, and then after traversing the rightmost level first we'll come back and then traverse the leftmost side. So sorry. So I'll first traverse here. I'll take a different color. Yeah. So I'll first traverse here and then to this traverse here. And for this I don't have a HL, so I'll traverse here. And I don't have a HL, so once again traverse here. I don't have a HL, so once again I'll traverse here. And I have reached the last stage, so I'll come back. Star HL, star left side. No, both of them are there. I'll come back, I'll come back, I'll come back. And now I'll go visit the left side. And now I'll once again go visit the left side. Yeah. And I'll just once again come back to this place. 0, 4, 4. And we'll go back. And I'll go to the left side now. And now I have to go to the right hand side first. Does this have any HL? Yes. So I'll go right. Does this have any right? No. So I'll go to the left. Does this have any right? No. So I'll go to the left. Again. And yeah, and I reached the final stage. So I'm appending it to the distant already. So 0, 4, 3. And I'll basically make my way back once again. Make my way back. And back. And now here, do I have a left child? Yes. So I'll go left. Do I have a right child? Yes. So I'll go right. Do I have a right child? No. Do I have a left child? Yes. So I'll go to the left. And then I'll insert this because it is the last level. And then once I'll come back. Once again I'll come back because there are no other children left. Once again I'll come back. And once again I'll come back here. And then now I'll go visit the left hand child first. And then right. And for this guy once again. And so on and so forth until. So this will be our traversal. And our traversal will basically start from root. I'll call the root first. After calling the root, it will call the right child first, and the right child will once again call its right child first, and this right child will once again call its right child first, and so on and so forth. And then once again after calling all of this, I will call the it will call the left hand side cell. So what do we need to know? Sorry, let's define a function f simple. And yeah, first I'll see if the index is you know that the index is -1 for everything except the leaf. So if the index is not -1, I'll append it to a list dot index. Else I'll reverse the right hand side first f of dot right. Before that I had to check if the node exists. So node if right node exists, I go to f of dot right, and if the left node exists, I'll call the so that's it for the sorting function. I will have to include a list L, and then I'll have to call f for the good node self dot and open and so on and so forth. And yeah, and then I'll return the list. So yeah, that will I think the sorting function is now okay. So let's go ahead and write the output for the code. So let's have a tree, basically a tree, and with the maximum number possible as 4, right? And to let's write the code once again to calculate the maximum number possible. Max is equal to 0 for again. So max, max, what is that? Example, and I in by next thing, say how to insert everything, right? So let's have the index, and then after inserting something, I'll insert it next one. And after I have inserted everything, I'll sort it. And I'll just print the sorted. So yeah, this should do it. Without any further order, let's run this. And the required output should be 0432. Let's check. 0432 So without doing anything, let's further change the code. I'll instead of I'll add 5 4, then I'll add something like 5 and now the output should be 043 043. For 0 it should be 5, then 6 5 6 0 3 0 4 3 with output. So let's check if it's 5 6 0 4. So yeah, that's the output, and let's just for, yeah, just to check whether the constraint whether it satisfies the constraint and stuff. Let's to check that, and let's put 1001. Then 1000. You know, basically that's the entire reason we are doing this code. So yeah, and it works as usual, as expected. And 1001 must be greater than the I mean the last one must be greater than the other one. So the order is pretty much cut. Once again. So yeah, I think that's everything for now. Thank you, and if you like the video, please do like, share, and subscribe. And if you want us to improve on something and want me to improve on something, please do leave something in the comment section or reach to us via our social medias. And thank you. We have a wonderful day.